helping you understand kind of what the details are in terms of how different anode materials and solid-state batteries degrade, with the goal of potentially enabling you to choose an ideal anode for your application. So I can't see anybody, but if you do have questions, feel free to jump in and interrupt and ask, or you can save them to the end, no problem. We have about 40 minutes here. I won't take that long with the slides here. I'll go 25 or 30, and then we can have a discussion. All right, I'm going to jump right into it. So which anode should I choose for my solid-state battery? So likely a lot of the audience already knows about solid-state batteries, so I won't have to spend too much time on this. But one of the reasons why there's a lot of excitement about solid-state batteries is the potential for improved safety because of the lack of a flexible liquid, as well as improved energy density. And that's where these anodes come in. The lithium metal could potentially be more stable in contact with the solid-state electrolyte. There are other anodes like silicon or other alloys that are also potentially compatible, which could boost energy density while also boosting safety for next generation applications, even hybrid electric flight and other long-range EVs. So there's been a lot of excitement. Probably some people in the audience work on solid-state batteries, maybe at various companies or in R&D. So it turns out when you replace the liquid electrolyte with a solid, things get quite complicated. And there's a lot that we've learned in the last decade, which we maybe didn't expect initially in terms of the challenges associated with solid-solid electrochemical interfaces. So I've listed some of these here. I'll cover some of these throughout the rest of the talk. One of the things that my research group at Georgia Tech focuses on, though, is trying to understand these various phenomena and understanding degradation mechanisms at interfaces in solid-state batteries, as well as other battery technologies. But today we're here for solid-state batteries. So we've been doing this for a while now, and we've learned a lot. And so today I'll be telling you about 3 different types of anode materials in solid-state batteries and really what limits their performance. And my goal is to, kind of provide this information. I'm sure some of you know it already, but the information is there so that we can maybe achieve some engineering strategies to improve performance. All right, so the main electrode materials are shown here. These are battery stacks, kind of schematics, showing a typical lithium-ion battery with graphite, and then 3 different cells with different other anodes. Here's a silicon-based anode, showing the decrease in cell volume when you go from graphite to silicon. Here's a lithium metal anode, where you have excess lithium metal present at the anode. And then here's an anode-free type cell, where you have no active material at the negative electrode to start with. You only have a current collector. So you can see the benefit of going from graphite to an alloy like silicon to lithium to anode-free, because you reduce the size of your cell. This directly translates to a higher energy density and usually specific energy as well. So that's why there's so much interest in this. You can get higher energy metrics. And that's shown here. So these are just some stack level calculations of cells with different sorts of anodes. Your typical lithium ion cell is down here at about 770 watt hours per liter, kind of in the optimized stack. Alloys can get you much higher, 1,000 to 1,200 watt hours per liter, and lithium metal can go even higher than that. So again, these are the motivations to get to very high energy density for mobility applications. So here's the 3 different anode materials, kind of classes of anodes that we'll talk about today. Lithium metal, anode-free, and then alloys. I'm keeping alloys general. Silicon is the most typical example of alloy-based anode materials for batteries, but there's also some other examples that can be used in solid state, especially, which are quite similar to silicon. And so again, we want to understand how the distinctive reaction processes of these different materials influence performance and maybe informs your decisions about which one to choose. All right, so we'll start with lithium metal. So lithium metal, again, was kind of the original motivation, or one of the main original motivations for pursuing solid-state battery. If we could achieve stable interfaces between lithium metal and a solid electrolyte, that could really boost performance of a battery system. There are 2 main challenges that are both interrelated when we use lithium metal anodes. The first is that lithium metal can grow dendritically through the solid electrolyte. It can crack and fracture the solid electrolyte and grow to short circuit the battery. And this is really a major problem when using solid state batteries. The second problem, which is related, is the fact that when you strip lithium, when you oxidize your electrode and you're transporting lithium in the ionic form through the electrolyte, if you do this too quickly, you can actually lose contact at the solid-solid interface and form voids. When you form voids, you then have a reduced surface area. When you recharge your cell, there's a very high local current density, which can cause dendrites to form. So these processes are kind of in a dance with each other. The voiding causes dendrites to form in this kind of a bad cycle. So this has been understood for a few years now. There's still some understanding that's not completely well known about dendritic growth, but the field and the community is working on strategies to overcome these issues. So I'm going to tell you about some of the things we understand. So my own group, we work on imaging of batteries, and we especially use X-ray tomographic imaging, where we can do three-dimensional imaging of full battery cells during operation. This is very valuable for understanding reaction mechanisms and degradation modes and other things like that inside active battery cells. So this is an example from our group of some imaging of lithium metal growth through a solid-state electrolyte. So this is a video that's being played over and over. This is probably 30 to 40 minute video that we're speeding up pretty quickly, as you can see, just a few seconds here. This is showing a solid electrolyte region. There's lithium metal. There's a lithium metal electrode on top of this solid electrolyte. You can't really see it. And then we're growing lithium, and it's growing in a dendritic fashion. It's growing and penetrating the solid electrolyte. It's actually fracturing it rather extensively. And you can see it grow here and then extend in kind of a filamentary form. So this process, filamentary or dendritic growth, is kind of a chemomechanical process where there's high stresses at a defect that can cause a crack to penetrate and grow, and lithium grows in the crack tip. This has been explained pretty nicely recently in a paper from the UK, from Peter Bruce's group in the UK. There's still some questions about the mechanical details of this sort of process, but the field has developed a pretty good understanding of why this happens. Something else that's kind of interesting about lithium filament growth. So some of you may be familiar with this typical test called a critical current density test. It basically involves taking a symmetric lithium solid-state battery and then applying higher and higher current densities until your battery short circuits, and the current density at which it short circuits is called the critical current density, and you want that to be as high as possible. So this basically, what this study from my group shows that, this typical test, which is widely performed, is really not that useful actually, because it varies a lot based on how you do it. And also something that was rather surprising is in these particular cells with a sulfide-based electrolyte material, ignoring this critical current density test, if you just applied a constant current density, even relatively low current density for a long enough time, we always short-circuited our cells. So the short-circuiting problem is really pervasive and a challenge to overcome. Okay, so the other side of the coin here, we have the short-circuiting on one side, we have contact loss and void growth at the lithium solid electrolyte interface as the other side. And these are some experiments that my group did to visualize this process. Again, these are X-ray tomography experiments. Here we're looking at inside a battery cell during operation, a lithium electrode in contact with a solid electrolyte up here. And we're stripping this lithium. So after a certain amount of time, the lithium has decreased in thickness, as you can see on the right, the exact same location. And what you see here at the interface are these kind of dark splotches, this dark contrast region. These are voids that have formed. So we've lost contact. And with these X-ray data sets, it's very nice because you can do full segmentation and analysis of all the voxels in the whole 3D space with time. And we can pull out, where at the interface voids are forming as we discharge the cell. And so that's shown here. Basically, this is a three-dimensional map of purple voids that are forming at the interface as we're discharging the cell. You can see that there's a lot of voids that grow in this particular cell. And this sort of characterization is useful because this is an example here. These contact area maps, we're able to map in 2 dimensions now across the whole interfacial area of an electrode where these voids are forming. And we can relate this to the electrochemistry. And in fact, what we learned from this study was that it's the isolated nature of these voids and the lack of contact that causes very high resistance in this type of battery with a lithium metal electrode. So even though we've only lost about half the surface area, which is still quite a lot, the resistance of the cell increases by many times that amount because of the current constriction around these voids, which is what this shows here. All right, good. So that's lithium metal electrodes. Of course, there's still a lot of interest in lithium metal around the world. There's lithium metal being commercialized in liquid batteries. There's lithium metal being commercialized in solid state batteries. I have high hopes for lithium metal. I think really careful engineering of the interface to control contact and to prevent dendrite initiation is really the key for lithium metal. And it appears that this has been somewhat successful in some of the commercialization efforts. All right, so we'll move on to the next type of anode. This is related. It's lithium metal based, but this is kind of a distinct type of anode. I refer to this as anode-free based solid state batteries. So what is anode-free? So in typical lithium metal cells, we use a lithium metal foil, some sort of composite cathode, maybe an MC. We have a separator and then a relatively thin lithium metal foil at the negative electrode. And as I just explained, we kind of have a fairly good idea of what limits performance in these excess lithium type cells. So an anode-free cell, otherwise known as a zero lithium excess cell, is quite similar. We have a composite cathode, a solid separator, but now there's no active material at the anode to start with. And when you charge the battery, you move some of the ions, you reduce them, and they deposit as lithium metal on this current collector directly. So you're still utilizing lithium metal as your active material, but the lithium is fully contained in the cathode upon cell assembly. And this is quite similar actually to a standard lithium ion battery where you have a graphite anode. But here we're utilizing lithium metal and electrodeposition as the active material. So the question when we started our work in this area was, what is governing performance of these anode-free cells? Is it the same thing as lithium excess cells, and how do we understand it? So we started working in this. We are developing anode-free solid-state batteries based on sulfide-based separators like our gyrodite that's shown here. One of the first things we did when we started this work was basically, can we deposit lithium on a copper current collector? It sounds very simple, but it turns out it's kind of challenging. You have to have very, very precise and controlled cell design. But we were able to really systematically control our cells and get good performance in terms of plating. You can see here we're plating up to 100 microns of lithium onto a copper foil in a solid-state cell. You can see that there as well. Here's an SEM image of lithium metal that's plated. So that's fine. Lithium plating is doable. But then what we see, which is really the most interesting thing, and there's a lot of data on this slide, but what I'll explain it to you. Basically, when we start cycling our anode-free cells, when we charge and discharge over a few cycles, what we always see is that they short circuit much, much faster than cells with excess lithium metal. That's shown here in half cells. That's shown here in full cells. When I say much faster, generally we see short circuiting in just 2 or 3 cycles in a half cell compared to many hundreds of cycles that can be achieved without short circuiting in symmetric cells with excess lithium. So something is causing a difference in behavior and causing much faster short circuiting over many fewer cycles in the anode-free case. And so we were kind of puzzled about this, but we have a hypothesis and a theory that's supported by some modeling and some other experiments. This is the basic idea. And this is pretty important, I think, for engineering effective anode-free cells. Basically, the key, we think, is that the very end of the stripping process ends up controlling behavior. And so I'll tell you what I mean by that. Here is a schematic picture of a cell after we've plated lithium onto a current collector from a salt electrolyte. Lithium's in gray. So now when we start stripping that lithium, we're removing it from the interface. And what happens at the very end of the stripping process is really key. So what we expect is, unless there's completely atomically uniform lithium stripping, we'll have some inhomogeneities, some non-uniformity at the very end of the process. There'll be some regions that have lithium remaining, like that's shown here, and there'll be some regions that are completely stripped of lithium where the current collector contacts the salt electrolyte. And this is the problem, because once we get to this situation, all of our current that we're applying to our cell is focused on these remaining lithium regions. And we know when there's a very high current density on lithium, we form voids. And so we end up with a situation like this, where you have these lithium regions that are small, but they form voids. And then when we reverse the current to charge, what we think happens is that's when dendrites form. These voids, at the edge of these voids, we have current concentrations and we grow dendrites. So this is a problem because it's kind of inescapable in a way, unless you're, atomically uniformly stripping lithium. And I don't think that's happening in anybody's battery. Here's some phase field modeling that supports this theory from a colleague and collaborator at University of Oxford. So the name of the game here is really extremely uniform plating and stripping across, many centimeters squared of area. For a full commercial battery, it would be, many hundreds of centimeters squared. So this is, I think, quite challenging. So there are some ways around this. I think modifying the interface is 100% necessary to achieve good performance. My group has done some work on understanding the impact of very thin alloy layers at anode-free interfaces. Specifically, silver and gold alloy layers, maybe 100 nanometers thick. They're deposited with PVD methods. We deposit these on a copper current collector and then test their behavior and try to understand how they're influencing degradation in anode-free batteries. So these are just some pictures. These are pictures of 3 different electrodes from 3 different batteries. We're looking at cross-sectional images that are created using plasma fib. So we're cutting into the cell. In the top, you can see a copper current collector that was in contact with solid electrolyte on the bottom, and then lithium has been grown. 1 milliamp hour per centimeter squared of lithium has been grown, and it's not good. This is just the first growth, but you can see it's quite non-uniform in thickness. The lithium, if you can look carefully, penetrates into the solid electrolyte in some regions. There's some pores in other regions. So this is not setting us up well for uniform stripping. In contrast, the silver and gold is much better. The lithium is much more uniform in terms of its growth and thickness. What's interesting, though, especially if you look at the gold, you can see these bright spots. These are particles. These are actually gold alloy particles. So this initially thin uniform gold film has broken up into lithiated alloy particles, and some of them have been dragged across the interface. So what this indicates is that these interfaces are not, static. They're very dynamic, and we have to think about engineering them so that whatever we put there can interact dynamically with lithium in a beneficial way during lithium growth and during lithium shrinkage. But what these interface layers do is, we'll have some more imaging there. I have a bunch of data here. I will not go into the details, but we did a bunch of impedance spectroscopy, and we found that these interface layers basically mitigate this voiding behavior over tens of cycles and really help with cycling. And in particular, they, at the very end of stripping, they can help retain contact and prevent void formation. So that's good. That's a start. They don't last, in our hands, they don't last more than 50 cycles or so. That was not really the intention of this study. We were looking at the fundamental mechanisms. I think to get to hundreds and hundreds of cycles, careful control over structure of the interface and initial contact is important, and potentially even stack pressure, dynamic stack pressure and temperature control can also be useful. All right, so that is lithium metal excess, and then now we just talked about anode-free batteries, and I'll spend the last 10 minutes here before we discuss on the last anode type, which is alloy-based anodes. So, of course, lots of excitement about alloys in general. Silicon is being commercialized. It is already a commercial product in some battery cells, especially in low quantities. The deal with alloys is that they host a lot of lithium. Silicon is the prototypical example, as I mentioned, but other materials like aluminum and tin and indium also alloy with lithium. They host so much lithium that they expand an enormous amount, much more than graphite, which reacts via intercalation. So silicon can expand up to 300%. This causes mechanical damage, volume changes. In liquid electrolyte batteries, this is a problem because you have these changes of the surface area with time as you cycle the cell, and that causes a lot of interphase SEI growth, and it can degrade performance. So actually, the solid-state batteries immediately offer a very intriguing possibility here, and it's that the interfaces are not so dynamic. The interfaces can be much more chemically stable because you don't continuously wet these surfaces like you do in liquid cells. And in fact, that's what we see. There's been some really exciting work in recent years. This is an example of a paper from Shirley Mung's group at Chicago. Here's some work from my group, where basically if you take unmodified silicon microparticles, which really don't work at all in a typical lithium-ion cell, they just fail within a few tens of cycles, you can get very good cycling performance out of these in solid-state batteries because of the much more stable interphase. The caveat is that pretty much all of these experiments have been at high stack pressures, which are not realistic for commercial batteries. But fundamentally, this shows that there's different behavior, there's possibility here. So we focused a lot on stack pressure effects and understanding the limitations of alloy-based anodes. Here's a study where we were actually measuring changes in pressure with cycling of these materials. And you can see here, this is just different alloy anodes. They all lithiate in similar ways, antimony, tin, silicon. You can see that full cells with these materials, solid-state batteries, there's a big increase in pressure, stack pressure during charge and decrease during discharge. And this is because of the volume changes within the cell. So recently in my group, we've been exploring kind of what's the fundamental limitation of these materials and how do we overcome them. So we did a survey of a bunch of different alloy materials. These are shown here, 12 different alloy materials. They all react in slightly different ways, but they store a lot of lithium. And we did a lot of electrochemistry. What's very interesting from these electrochemical results, and again, there's a lot of data, so you don't have to really look at all this. These are half cell discharge charge curves. The main thing to draw from all this data here is really the amazing performance of indium. So indium exhibits almost 100% Coulombic efficiency in solid-state half cells. It has very high lithium diffusivity. You could insert lithium and you can remove it with very high efficiency. All these other alloy materials, it varies quite a bit, but generally there's much, much lower efficiency. This is for two reasons. In solid-state batteries, this is because of contact loss and interfaces, but it's also because of lithium trapping in these sorts of materials. Once you diffuse lithium in, sometimes when you delithiate, lithium can be trapped within the structure, and I have some evidence for that in a few slides. Actually shown right here. So there's the question is, why is indium so good? Here's some fib cross-sectional images of various alloy materials. This is aluminum. This is a lithiated aluminum material. Aluminum reacts with lithium like silicon. When you delithiate this material, what you find is that this is the bottom of the electrode here, the electrolyte interfaces right here. You delithiate it part way and you have pristine aluminum that forms, and you can't get any more lithium to diffuse through this aluminum. It turns out that the lithium diffusivity in the pure electrode is usually quite low, and so there's this kinetic trapping effect. You find this with aluminum, you find this with tin, you find this with many of these materials. Indium is a special one, and it doesn't really show this trapping effect we've found. You have this lithiated phase here. When you delithiate, this lithiated phase shrinks but retains contact with the salt electrolyte. So big picture here, the microstructure evolution of your alloy matters. The contact retention, but also this trapping effect, mitigating the trapping effect, is quite important. This is the case for silicon as well. I just mentioned silicon behaves in a similar way. There's always some lithium trapping in silicon. This is just some data from full cell cycling showing that indium also can be used effectively in full cells. Notable, of course, that indium is very expensive. But we've taken these sorts of understandings and we've actually developed a pretty new concept for solid-state battery anodes, which behave quite well. And the idea here is to, instead of slurry coating particulate electrode structures like we do in lithium-ion cells or like many people do with solid-state batteries, we focused on trying to develop dense metal foil alloy anodes. And the benefits of the dense foils are, number one, you don't have any other components, so it's pure capacity. Number two, they can be quite cheap to manufacture and to process. You do away with slurry coating, which is great. So what we focused on is aluminum-based foils because aluminum is widely abundant, recyclable, sustainable, and very cheap. We're mixing it with indium, though. So indium, I mentioned, is quite expensive, but if we use it in small amounts, it turns out that we think the economics can work pretty well. We create these dense foils that are 95% aluminum and approximately 5% indium by molar quantity. And we roll these out to form these particular microstructures where indium is dispersed in the aluminum in these layers. So you can see this is a cross-sectional image of one of these foils. Here's a picture of a small foil. So we incorporate this into solid-state batteries and we get very good cycling performance. This particular cell is showing 500 cycles at relatively high areal capacity, decently high current densities. This is a full cell with an NMC cathode. This is at very high stack pressures, 50 megapascals. I hope that I have some lower stack pressure data too. I don't remember, but we're testing these at low stack pressures too. And we modify the interface in some ways to get to low stack pressures effectively. The real benefit of this sort of multi-phase alloy is the good stability, but most importantly is the initial Coulomb efficiency. So pure aluminum traps a lot of lithium, as I mentioned before. The Coulomb efficiency is only about 60 or 65%, really terrible. With this two-phase microstructure, we can get 85, even higher than that percent as the first cycle. And this is because of this two-phase network. So the lithium indium phase, which you can see in these cross-sectional images during kind of a charge and a discharge, acts to transport the lithium very effectively throughout the structure. And over many cycles, this is the case. We've characterized that here with other methods. So this is in effect a composite electrode, but we're only including metals in the composite, and it works quite well in solid-state batteries. It avoids a lot of the SEI growth that's found in lithium-ion liquid electrolyte batteries. All right, so I kind of explained this already. At this stage in this project, we're scaling to pouch cells, and we're also, I mentioned we've developed some interfacial coatings that help retain contact and can enable performance at low stack pressures as well. All right, so that's my presentation. I'm happy to chat a little bit if there are questions. I talked about a number of integrating various alloy lithium metal and anode-free type anodes in solid-state batteries, and some of the distinctive really limitations of each, with the idea that maybe we can overcome some of these limitations with various engineered strategies. So here's my group at Georgia Tech. Happy to discuss, take any questions, or talk further.